All right, so before we can carry on looking at exponents, specifically rational exponents, we've got to go and look into radicals first, because you've got to know about radicals before you can work with rational exponents. Before you can work with radicals, you've got to know what makes up a radical. So there are three parts to what we call a radical. And the first part right here, this n, is called the index. And what that's going to tell us is how many times does the answer need to be multiplied in order to get this number. So you've all seen the square root of 4 before. The index right here, even though it's not shown, it's assumed to be a 2. So what that tells us is we're looking for a number that multiplied against itself, is going to give you 4. So we know that 2 times 2 is going to equal 4. So the solution to the square root of 4 is 2. The number that you're trying to figure out, or the number that you're trying to get to when you do this process here, this is called the radicand. And then the radicand sits under the radical sign. Now this index could be anything. It could be 2, it could be 3, it could be 4. Really what you're looking for is, so in this section we're going to do problems number 1 and 2. And all we're doing is we're looking to simplify the radicand. We're trying to make this into as simple a radical as we can get it. So one of the things that you definitely need to know is that you can take a radical and you can actually break it down into component parts. So you can look for perfect square factors, you can just look for factors. You can do a whole lot when you're working with a radical. So we want to simplify this as much as we possibly can. So the easiest way to do that is to look for perfect square factors. And to look for perfect square factors, I'm just going to list out the factors that I know for 160. So for 160, I know I've got 1 and 160, which doesn't really do me a whole lot of good because that's not a perfect square factor to begin with. Then 2 and 80, 3 will not go into 160, 4 goes in 40 times, 5 goes in 32 times. Let's just make sure that I'm right here. 5 times 30 is 150, 5 times 2 is 10, 150 plus 10 is 160. Then 6, 6 will not go into it, 7 will not go into it, 8 will go into it 20 times, 9 will not go into it, 10 will go into it 16 times, 11, 12, let's see, will 12 go into it? No. 13, 14, 15, and then we get back to 16. So now I've got a list of factors, or a list of factor pairs for this radicand. So what I'm looking for is, what is the biggest perfect square factor that I've got? And what I mean by a perfect square factor is, if I take the square root of a number, and it gives me just a plain old integer. So if I take the square root of 4, I get 2. If I take the square root of 9, I get 3. The square root of 16, I get 4. But if I were to take the square root of 7, I'm going to get a decimal. So the square root of 7 is not a perfect square. But 4, 9, 16, 25, 36, they all are. So I'm looking for, what is the biggest one that I've got? So what I'm going to do is I'm going to start by going down this side of the list and see if I've got any perfect squares on this side. If I don't have anything on this side, then I'm going to continue by going up that side. If I don't have any perfect squares, then what that means is this is simplified as it can get. So starting at 160, I know that 160 is not, 80 is not, 40 is not, 32 is not, 20 is not, but 16 is. So that's the factor pair that I want right there, 16 and 10. So what I can do with this radical now is I can change this from the square root of 160 to the square root of 16 times 10. You are allowed to do this. There's no issues with doing this process at all. Now the next thing that you can do if you want to is you can actually take this one radical and break it into 2. So instead of saying the square root of 16 times 10, I can say the square root of 16 times the square root of 10. Now I can take the square root of 16, which is 4. And then I'm left with the square root of 10, which cannot be simplified at all. So the simplified form of the square root of 160 is 4 square root of 10. So the important part to this, the very first step, is to take all of those factor pairs and then figure out where do you have a perfect square factor at. In this case, it was 16 and 10, which allowed me to break this radical down. For problem number 2, we're going to be asked to do a little bit more with this. So we've got the square root of 54 into the 7th. We got a couple of parts that we've got to go through, but let's go ahead and start with our factor pairs. So we've got 1 and 54, and then 2 and 27, 3 and 18, 4 will not go into 54, 5 will not. We get 6 times 9, 7 and 8 will not go into 54, so then we get back to 9. So now we know we've got all of our possible factor pairs. Then we're going to go down the right side. 54 is not a perfect square, 27 is not a perfect square, 18 is not a perfect square, but 9 is. So that tells us that our factor pair is going to be 9 and 6. So I can rewrite this now as the square root of 9 times 6 into the 7th. Then if you want to, and again, you don't have to do this, but whichever you feel more comfortable with. If you're okay working with a single radical, you can just work with a single radical. But if you don't like doing that, if you'd rather break this up into different parts, you can do that. So this becomes the square root of 9 times the square root of 6 times the square root of n to the 7th. So now we go, take a look at that square root of 9. That becomes 3. Square root of 6 is as simplified as it can get. And now we've got to work with this into the 7th. Okay, so this is where it gets a little bit more complicated. What we're going to do, I'm going to blow this up a little bit over here. We've got the square root of n to the 7th. So what I want to do is I want to look at what is my index. The index is going to be a 2. What I'm going to do is I'm going to divide the exponent that's attached to that variable by 2. So if I do that, I get 7 divided by 2 equals 3 with a remainder of 1. So this is what's important. Whatever the quotient is, that 3, that's the number of n's that I'm going to pull out of the radicand. Whatever the remainder is, that's the number of n's that are going to be left inside of the radicand. So what this means is that I'm going to have n to the 3rd coming outside of the radicand, or out of the radical, and then one single n left inside of the radical. I can then combine these two, 3n to the 3rd, and then I can combine my radicals back together and get 6n. So your solution is 3n cubed square root of 6n. Again, the reason why this happens is because I can basically break this into the 7th down into n to this n squared, n squared, n squared, and then n. If I have 3 n squareds, well, the square root of n squared is n, so I can pull 3 n's outside of the radical. So again, if you understand this, go ahead and just shut the video off right now. If you don't understand how this works, let's take a look at it. You've got the square root of n squared times n squared times n squared times n. So here's what you can do with this. You can say, I've got a square root of n squared. Well, what's the square root of n squared? It's n. So I can pull 1n out. So that's gone. What's the square root of n squared? It's n. So I can pull that one out. What's the square root of n squared? It's n. So that one can come out. Square root of n, I don't have enough n's there to be able to pull another one out, so it's got to stay inside the radical. So that means that I've got 3 n's sitting on the outside that are multiplying against each other. So n times n is n cubed square root of n. That's where I get this n cubed from and this n from. And that's how you get to that solution.